Swayam Prabha. Digital India. Educated India.
Okay, so welcome back. What we started out in the last class is basically now study about Kolmogorov length scales, and what we're trying to do here is to understand, is to sort of quantify, right, the length scales, right, of the various turbulent phenomena that we are seeing in a turbulent flow, in the sense that what sort of eddies are present given the length scale, what is the kind of dissipation of energy that we're talking about, or more appropriately, what is the kind of energy transfer that we are looking at, right, given a certain RE, given a certain length, how do these things, so I mean, can I say for sure that if this is my length scale that I'm looking at, right, there is going to be a dissipation of energy, right? Or if can I say that, you know, in this particular length scale, the RE of the eddies given a certain characteristic length is going to be so and so, right? So what is the RE of the smallest eddy size or the largest eddy size? How do they compare with the flow itself, right? So that we started doing all of that, and here actually, so we defined these things here, right? So we said at a high Reynolds number, say characteristic velocity and length is denoted by, you know, a superscript plus, and the corresponding Reynolds number is large, right? Now, of course, as has been proposed by Richardson, the turbulence consists of eddies of different sizes. Right. So let's just say for the characteristic length of, you know, such eddies is L, corresponding velocity and the time scale, right. Now then we also said that yeah, well, what exactly is an eddy? Then eddy is essentially turbulence, which is sort of which is in a very small length scale, which is restricted, is that the word, right word? Yeah, so localized, okay, with a region L. Now, for the largest size of the eddy, let's the characteristic length is L naught and velocity is this, right? So we did that, right? And then we were able to say that L naught is essentially comparable to, so L naught is comparable to L dash here, right? So if you have a fully turbulent flow, right, then the largest eddy size, you know, the characteristic length, right, of the largest eddy size, of the largest eddy, okay, is going to be comparable to the characteristic length of the turbulent flow itself, okay. So it could basically be that large. Now we know that there are several sizes of this which can be present. So now the largest size is comparable to the characteristic length of the flow itself, right. In that case, what should be the smallest, right? What should be the smallest? So that seems to be, you know, the question we'd like to answer right now, okay. Now so like we said here last time, so the size here is so size here is L naught, and so which is basically comparable to L plus, which is the characteristic length of the turbulent flow itself, and U is the order of RMS turbulent intensity, right? This, and this is also I haven't written this here, but this is also comparable to the U plus, right, which is essentially the velocity, right, of the characteristic velocity of the turbulent flow itself, right. Okay, so right, so the largest eddy size, right. So length scale as well as velocity is comparable to that of a fully turbulent flow. Okay. Now, so let us say then RE right, this and this is large, right. So in this case, therefore, the Reynolds number, corresponding Reynolds number of the largest eddy is also large and comparable to the Reynolds number of the fully turbulent flow itself, right. So this essentially, if you see, therefore, this implies direct effects viscosity are small, right. So we can neglect this as well. You can neglect. Okay. Now the point is, okay, so now fine, we have very large eddies, but these large eddies will not remain so, right. They will start breaking up, right. And in that case, what happens to the contained energy? That needs to be redistributed as well, right. And how long will this breaking up continue? How far will this go? I mean, what will be the criteria? It will need to stop sometime, or will it not? Right? That's the question we're trying to answer here. So large eddies will break up, right, as they will be unstable, and transfer their energy to the smaller eddies. Okay. Let me write these. These are notes. I kind of will write this down. Okay. So large eddies break up, as they are unstable, okay, and transfer the energy to smaller eddies, right. Now, till how long? I mean, okay, now then let's just say, right, okay. So this is for any any eddy, okay, in the turbulent flow. So large eddies will break up, okay, because see, these are unstable, so they will break up and transfer the energy to smaller eddies, okay. And when will this stop? Well, this will stop when this Reynolds number, the corresponding Reynolds number, is small enough that there is stability and they don't sort of need to break up, right. And in here, like I said, the direct effect of viscosity are small, right. So it is, so the Reynolds number, this continues, right, to smaller eddies. This process here, okay, this process, that larger eddies break up, right, and transfer the energy to smaller eddies. Now that continues, right, till, right, this Reynolds number, basically the corresponding Reynolds number is small enough such that the flow is stable, right. Small enough so that the flow is stable, right? And there is a dissipation of energy can happen. Right. So this is so basically that. Okay. So now that we've defined sort of some basic length scales, we're trying to understand this, right? So we said there is we denoted that by the superscript plus. So that is essentially the length scale of the flow itself. Then we defined another length scale, which is for any arbitrary eddy, and which the ones without any subscript or superscript. And then we said the largest eddy, which is denoted by subscripts naught. So L naught, U naught, etc. T naught. Okay. So and then we said what we saw that the characteristic length and the velocity of the largest eddy is comparable to that of the fully turbulent flow itself, right? And now the process is such, the energy cascade, is that the large eddies will break up and transfer the energy. It has to be redistributed, right, to smaller eddies, right? Now the point is, how long will this continue? This will continue till the Reynolds number corresponding to any eddy here, right, here. So that is small enough such that the flow is stable and the dissipation of energy can happen, right. So okay, right, now let us get into, so now let us see specifically what Kolmogorov hypothesizes, Kolmogorov's hypotheses. Okay. Now he says something about a few, I'm going to jot it down, a few points as he sees. Okay. So length scales essentially. Okay. So essentially, okay, so the smaller eddies, right, and the corresponding length scales, and when this happens and what will happen, is it one just band or a couple of bands inside of it. So this is something that Kolmogorov proposed, right, and hence bears his name. Okay, so we're saying Kolmogorov length scales. Okay. All right. Now he said something about local isotropy. Right. So essentially, if we are looking at this, so now the point is, I need to identify length scales where I have the smallest eddies operating. So that's my objective now. So what changes? What is it that changes, right? When I have further energy is not being transferred, but is being dissipated. Right. So that's when I have reached the smallest eddies, right? So so energy is not being transferred further, instead it is being dissipated, right? It is small enough such that further transfer of energy is not happening, the corresponding Reynolds number, etc. Okay, so let me write this down. So essentially what he's saying is that a sufficiently high Reynolds numbers, right, in the small scale turbulent motions, right, how do I, now the point is, how do I define this? When I say small scale, what does that mean? So this length of any particular, so a particular an eddy, L is less than L naught basically. So L is less than L naught is the largest eddy, that's all. Okay. So right. So in the turbulent motions, right, this is the length scale that we are talking about. Okay. So, at sufficiently high Reynolds number, right, the local, so you see the small scale turbulent motions or the localized turbulent motions, right, are show isotropy, are statistically isotropic. Okay. So, if I were to write this down, let us just say L, yeah, well, this is small scale basically. So, this means small scale. Okay. So, at sufficiently high Reynolds number, okay, so essentially this, the small scale turbulent motions, right, are statistically isotropic. Okay. Also, this word, this, when I say local isotropy, it itself also refers to small scale. This also actually, yeah, so I mean I can actually write it like this. So, local, the moment we say local isotropy, so this is Kolmogorov's hypothesis that, you know, any small scale turbulence is locally isotropic. Okay. So, statistically they are isotropic, okay, at sufficiently high Reynolds number. So, therefore, the moment I say local isotropy, it also pretty much means that I am looking at small scale turbulence. Okay. All right. Now we will put some numbers in and let us see what we get. Okay. So, let us just say this will be the length, we will write something, we will explain slightly later on. Okay. So, let okay, let the length, we take a length scale. Okay. This, right. So, let us just take a length scale which is L, right, EI, and such that right. So, let us just say this. Okay. So, this length scale, you know, is less than 1/6 of L naught, 1/6 of the largest size of an eddy, right. So, let's just say this is a length scale and I have, you know, taken this, then so in the sense that just now as I said local isotropy. So, when I said local small scale, you know, so now again quantify it. What is small scale? So, small scale is 1/6 of the largest eddy size. Okay. So, essentially what I am saying is, so if, so this essentially means that if length, right, is less than this, right. So, we have isotropic small scale turbulence. Okay. So, we have isotropic small scale turbulence. So, isotropic small scale turbulence, and if it is larger than this, then it is anisotropic large scale So, couple of things here. Number one is that the moment we say local isotropy, the moment so local isotropy essentially means we are dealing with small scale turbulence, right. So the moment when we have small scale turbulence, how big or small is the small size? It is 1/6 of the largest eddy size, right. So that's why this L. So if I have small scale turbulence, I have isotropy. Okay. However, if I have large scale turbulence, right, then we do not have isotropy there. We have an isotropic large scale turbulence. Okay. All right. So now another two things that I will write here before I write out is hypothesis. See, as energy passes down the cascade, the directional information of the large scales is lost. Okay. So as down the cascade, right. Now, directional information right of the large scales okay. So the large eddies have broken up, energy is being cascaded, energy is being transferred, right, to the bigger to the smaller, right. But then by the time as it passes, this is not something which is remembered or which is stored in memory of the flow. You know, it's not like, so in the sense that this is not, we are not sure if this is the way it will break up and this is the way energy will transfer, you know, if I see another turbulent flow. So this directional information is lost. So that's what we mean of the large scale is lost. Okay. And also all geometry related information is also lost, right, as energy cascades. Okay. Now all geometry related info, for example, mean flow, boundary conditions, okay. So as energy is cascading from larger eddies to the smaller eddies, right. So this directional information that, you know, it came from say A to B, you know, B to C, etc. Now that information is lost, right. So if I look back, I will not be able to figure out how the energy had come from, what trajectory the energy the transfer had taken. That information is lost. Also geometry related info like mean flow, right, the boundary conditions is also lost. Okay. So therefore, so this therefore means that I have say a couple of turbulent flows, right, and I have an energy cascading going on in all of these. Right. Now it is going to be very difficult to say how the energy cascaded in a particular, you know, example of the turbulent flow compared to the other two. You know, it will be very difficult to say because the information is lost. Okay. However, once all this cascading is done and they reach the smallest scales, then that is where now flow is going to be, I mean the energy is going to be dissipated, right, and that therefore is statistically, you know, so although I cannot I do not have any information, and I cannot compare the way the energy cascading is happening between large eddies and two smaller eddies. For all these things, that information is lost. Right? So we do not know for sure how that has happened. However, once we reach the small scale turbulence, that has a uniform or universal or similar motion, right? So that is comparable, the small scale ones. Okay, so this essentially means statistics of small scale small scale motions okay, the statistics of the small scale motions, right, are universal well, it could be same. Okay, similar at high RA right. So although the energy cascading, we do not have any information about the large scale turbulence, we do we can however figure out what's going on with the smaller length scales and small scale turbulence, and that seems to be universal or similar at high Reynolds number. Okay, so now we are here where we can write the first hypothesis. Okay, I think I should. Okay, I might as well write it here. So here the first hypothesis. So we write this as first right. Okay. So I'm going to write this down first, see if it makes sense. In every turbulent flow, right, at sufficiently high RA, okay, the statistics of the small scale motions the statistics of the small scale motions right. Essentially, when I say that, okay, so this have a universal form, right. That is uniquely determined, right, by. Now this is very interesting. So now we have said we have kind of put some at least numbers as to how small, etc., right. Now what the Kolmogorov hypothesis says is that in every turbulent flow at sufficiently high RE, the statistics of the small scale motions, right, have a universal form, right, and this is where he says that this is something that I can uniquely define using two parameters, which are the kinematic viscosity and dissipation rate, right. So, this one, the nu is of course the kinematic viscosity, this is a dissipation rate. Okay. So, now the moment we get onto the length scale, right, where we are basically looking at small scale turbulence, right. So, this is what we are interested in, right, and this is where Kolmogorov provides quantification, and hence the name Kolmogorov sizes. Now, so let us see what we will do. So, what we are basically saying is that if you have nu and if you have epsilon, right. So, we can, using these two, we can have characteristic length scales, velocity scales, time scales for this case, right. So, in this case what we have, how can we do that, right. So, let us just say, so we will define three things. One is a length, one is a one is a velocity, and the other is time, and we are going to generate those that using these two variables, using these two variables. Is that right? Okay. So, then let us do that, right, in order to do that. So, let us just say first is the length, right. So, I am going to write that, let us just say eta, right, is equal to so this is the length, okay. Next is the velocity, okay, is epsilon okay, and we have a time scale. Okay. So, that is the time. So, essentially what we are doing here is we are trying to figure out specific length scales for small scale turbulence which are dependent on gamma and epsilon, right. This is basically Kolmogorov's hypothesis. Okay. Now, here if you see this, if you see this, then RE is equal to okay. So, in this case okay. So, therefore, if I write down the length scales in such fashion, I see that my RE is also very small. Now, this is it's like a cross check. We are trying to see whether the Reynolds number is fairly correctly being evaluated, right. Okay. Now, if you just look at this, see here epsilon okay. So, u eta by this thing, you can see that. So, this is nothing but Okay, so therefore, well, this is something that it's coming from this. Okay, so now or okay, I just take these two, right? So I just take this, and then watch. Okay, so okay, so therefore, if I use it this way, I can see that I actually have velocity over length is equal to 1 by time. So it's fine. So what we're doing here is fine. It's consistent. Okay. Now let us use this scaling. Use the following scaling, right? So let's just say okay, let us use the scaling here. Okay, so if I do this, right, epsilon, so I'm writing that in terms of the highest, the largest eddy, right? Okay, so in that case, so what we're going to do is use this scaling, right, and use it onto 1, 2, and 3. Use it onto 1, 2, and 3. See what we get. Okay. Okay. So our eta, for example, is given by right. So from here is eta to the power 4, which is this, right. But we have said that epsilon this. Okay. So I'm going to use that in here. I'm going to use that in here. Okay. See if I do that. Is okay, why did I have this 4 in here? Okay, this is essentially just epsilon. Okay, so I've just taken raised both sides, this entire expression to I've raised it to power 4. That's all. So you have a to the power 4 minus is equal to the right hand side, just in the bracket. That's all. Okay. So from here, I'm going to try and input this where, right. So this epsilon is basically u naught cubed by, this is how we've defined it. Okay. So in that case, this, so I can write this as gamma cube, right, this by this. Okay. So if this is thing, so let me see if I can write this now. So let's just say by L naught. Okay. So I'm going to do this here. Okay. Okay. So or okay. So this again is equal to okay. This, right. So now again I'm going to take raise both sides to 1 by 4. No, it's fine. So okay, so now then eta, right, bring down L naught. This is equal to okay. This. Okay, so this one is actually right. So or right is this right. So do you notice what's going on the right hand side? It's 1 by RE, right. So or this. Okay, so we got one relationship here, right, this way. This also I can write this, or eta, right, eta by L naught is equal to okay, that's the dependence on Reynolds number. Okay, so now I'm going to call this as that. Okay, so similarly we'll go ahead and do it for, so this one we got using the length scale. So let's go and look at the velocity scale and see what we get, right, and how we can incorporate this. Okay, so now let's go to the next page. So this is equal to this, right. Now then, and we've also defined epsilon to be okay. So therefore epsilon gamma. Okay, so well, I can sort of skip the whole calculation, let you do it, but I think you should try it. Okay. Okay, so then so I need a length scale actually. So U this thing, right, okay, so this okay, so then I can okay, so right, or okay, okay. So we have one of these in here, okay, U naught L by this thing gamma, right, and then you have Okay, so therefore, okay. Okay, so this one, of course, so this is equal to RE cube okay. Okay, you can do this yourself and sort of cross check as to what I'm doing is right or wrong. Okay, so therefore, so essentially I wanted another value like that. So therefore, so this is okay. So we have that, right? So therefore, so finally I can write that U eta by U naught is equal to okay, I missed this one here. Okay, so this is equal to 1 by RE. So therefore, this is equal to RE okay. That okay. So that would be the okay. Is that 3 or yeah? That was 4. So this is actually 5. Okay. So U eta by U naught is this. So finally, I'm going to just write this here. So tau eta okay. So that should be okay. So so we've basically figured out, as you can see here, right? As you can see here, sorry. So if I have a length scale, right, for the smallest times, for the smallest eddies, right, the length scale, right, as a ratio of the length scale, which is corresponding to 1/6 of the largest size of the eddy, right. So L naught is, which is comparable to the full scale, to the full flow for the fully developed, turbulent flow, right. So we have expressions for these, right, in terms of the RE, right. So the next thing is also this U naught. And finally, we also have the time scale. So these all can be represented these all can be represented, right, for a turbulent flow, but we're looking at small scale turbulence. Okay, so I think I will stop here. There's a little more to go on these lines, and then we will get into the second hypothesis. Okay, so for now I will stop. So thank you.